Hello again. This is Math 2270 coming to you from the College of DuPage. And the title of this lecture is Picard's theorem. And this is actually just one of Picard's theorems. And in fact, there is more than one Picard's theorem that is named after him. But this is the one that deals with differential equations and the existence, uniqueness, and proof commentary for Picard's theorem. And as always, please be an attentive learner while watching this video. So let's state Picard's theorem for the existence and uniqueness of a solution. So we consider an initial value problem, and this is dy dx is equal to f of xy, and the initial condition is that y evaluated at x0 is y0. Now the if part of the theorem is if f and the partial of f with respect to y are continuous functions in some rectangle R, and you can see that it is a rectangle because x runs from a to b and y runs from c to d, that contains the point x0, y0. So x0, y0 has to be within the rectangle. Then the initial value problem up here, and notice that x0, y0 was inside the rectangle, has a unique solution in some interval, and this is the interval of validity, and we go about x, and it goes, it's actually about x0, and it goes from x0 minus delta to x0 plus delta, where delta is a positive number. Now, this is not the first existence theorem you've seen in your math career, and we are going to talk a little bit about the proof and the proof technique. And I'm going to provide information if you want to dive deeper into that. It is actually one of the highlights mathematically for this course. In addition to the statement, which talks about first order differential equations or first order initial value problems, it provides a context for higher dimensional differential equation existence proofs and similar existence proofs for systems of first order differential equations. Kind of a big deal. Now let's begin by considering an earlier existence proof that you have run across. So back when you were taking Calc 1, you studied the intermediate value theorem for continuous functions, which states that if f is a continuous function, it means you can trace it without ever lifting your pencil over a closed interval, AB, and it does have to be a closed interval, and the domains the domain of the function is from A to B, and it has values of f of A and f of B at the endpoints of the interval. Then the function takes on any value between the values f of A and f of B at a point inside the interval. And so the theorem could be explained graphically just looking at this. Now you notice that here is f of A and here is f of B, and this particular continuous function actually takes on this value y equal k 3 times in that interval. So what we're really saying is that there is it takes on any value, at least one. But another way to say it is, if k is any value between f of A and f of B, then either then there exists a number c within A and to B such that f of c equals b. Now there exists at least one number. As you can see, there could be more than one number. But you see, we're declaring the existence of such a c. Now you should note that a non-continuous function can satisfy the intermediate value property. Here, I'm showing you a discontinuous function. Here's the point of discontinuity. But what happens is this does satisfy the intermediate value property because any value, there's at least one value that catches it. So you see, we can have non-continuous functions that do that. But not every function does satisfy the intermediate value property. So here's an example of a discontinuous function that doesn't, because this value here, the blue value across here, the function doesn't cross that. And so that not every function will satisfy the intermediate value property. And you may remember that the proof of this calculus 1 theorem gave no generous clue about how to find the point. At least the statement didn't tell you anything about how to find the point. Now we're going to talk about a different type thing, but this also arises, and you may remember this from your algebra course and maybe not, but this is talking about solving equations using iteration. And so what we see is that approximate solutions to more complex equations can be found using a process called iteration. Iteration means repeatedly carrying out a process. To solve an equation using iteration, start with an initial value and substitute this into the iteration formula to obtain a new value. Then use the new value for the next value and so on. So here is an example. So suppose we're looking at the equation x cubed plus 5x equal 20. And if we take x0 to be 2, we would see that 2 cubed is 8 plus 5 times 2, so we get 18. So that's not exactly 20, but it's not a bad guess. So what we're going to do is we're going to take and we're going to solve this for x, and we'll say that, so we're going to take this equation and we're going to look at x sub n plus 1 is equal to the cube root of 20 minus f of x sub n. So you see, if you know the nth value, you can determine the n plus first value. So let's see what happens when we take the initial value, x0 equal 2. So we plug that in to this, and what will happen is we will find that x1 up here is equal to, I'm putting 2 in here, will give me 2.154. And then I take the 2.154 and substitute it in to get x2, getting this. I get x3 by substituting the 2.097 in, and so on. Now I keep working, but if I wanted to only have 3 decimal place accuracies, you see that I've reached 3 decimal place accuracy here. So since x6 and x7 give the same value to 3 decimal places, we can stop the iteration. The solution to the equation is that, to 3 decimal places. Now, I should tell you that this doesn't always work, but you get an idea of such an approach. And in fact, this is used in the proof of Picard's theorem. But before we get to talking about the proof, let's just take a couple of examples of applying Picard's theorem, and I will expect you to know how to apply Picard's theorem. So let's consider up here, shown by equation 11, 3 dy dx is equal to x squared minus xy cubed, and y of 1 equals 6. So does theorem 1 imply the existence of a unique solution? Well, we can put this in the form dy dx is equal to 1/3 of x cubed minus xy cubed. And so both the function f of x as well as the partial, if we take the partial derivative of that, we will get minus x squared y. So both of these functions are continuous in any rectangle containing 1/6, which was the initial value. So the hypothesis of theorem 1 is satisfied. Therefore, it follows from theorem 1 that the initial value problem has a unique solution in an interval about x1 of this form. And although I don't ask you to find the interval validity in this particular problem, I sometimes do, and you should be aware of that. Okay, so that is one example. Let's look at another one. Now, if we look at this initial value problem, dy dx is equal to 3 y to the 2/3, and y of 2 is equal to 0. Does theorem 1 apply? Well, here, theorem 1 is not going to apply because the partial of f with respect to y does not exist, does not defined, it's not continuous when y equals 0. So the theorem doesn't apply, so we can't use the theorem. Now it does turn out that this initial value problem has not a unique solution, but it has more than one solution. And I'm not going to do that now, but this is an example where the theorem does not apply. Now, in example 9, though, suppose that the initial condition was changed to be y of 2, not equals 0, but equals 1. Now, then, f and the partial of f with respect to y are continuous in any rectangle that contains 2, 1 that does not intersect with the x-axis. So it follows from theorem 1 that this new initial value problem has a unique solution in some interval about x equal 2. So you see the initial condition matters. It matters big time. Now, before we discuss the idea behind successive approximations that's used, let's first express the differential equation that we had, and remember that that was y prime equal f of xy, and y at 0 equal y at x0 equals y0, and suppose f is continuous. Then there's a solution. Well, we could just integrate both sides, and we're integrating with respect to x, but here I'm showing it as t. Now, if we did that, when we integrate y prime, we're going to get y. And on this side, when we integrate it from x0 to x, that's what we get. Because if we were to take the derivative of this, the derivative of a constant would be 0, and the derivative of this integral from the fundamental theorem of calculus is going to be taking x and putting x in there. And so that is f of xy. And so you see this is a solution to the integral equation, and the integral equation is equivalent to this. And notice that if you put x0 in for x, that means I'm integrating from x0 to x0. That means this is 0. And so this is y at x0 is equal to y0. So this IVP is equivalent to the integral equation. Now that seems convenient and useful, but upon further inspection there could be a couple of problems. The integral is not well defined unless we know that a solution exists, because we can't integrate something where there is no solution. And the integral equation could be very hard to solve, except if we have very elementary initial value problems. But the thing to keep in mind is this format right here. So what we're going to do is we're going to define an operator, and we'll talk about operators later in the course, that maps the function y to the function t of y, which is this. Then the integral equation is simply the solution to y equal t of y. That means that y is what we call a fixed point of the operator t. Now, to find fixed points, approximation techniques are often useful. That's actually what happened in that algebra equation that I was showing you. Okay, so what we are going to do is we're going to start by saying y0 equal y0, my initial value. But then we're going to use the iterating equation yn plus 1 of x is equal to yn of x plus, and this is going to be the integral from x0 to x of f of t, and then I'm going to have yn of t. So you see I have a recursion thing, because I can go from the nth solution to the n plus first solution in the sequence. And we get a sequence of functions, y0, y1, y2. And if this sequence converges, it can be shown, and that's what the proof is about. The limit function will be a fixed point of t, and in fact this will be what we're looking for. Now, I have taken a paper by this young mathematician, Denise, and I have attached this. It's about an 8-page paper, but it really talks about this, and you actually could understand this if you read it. And so this is something I would encourage you to look at. But before we do that, let's just talk about using that to solve an easy differential equation. So here we're starting with the IVP, y prime equal 2y, and y of 0 equals 1. Now, this is continuous, and the partial with respect to y is also continuous. It's just 2. So the theorem does apply. So we start with y1 is equal to this 1 plus I'm integrating y0. Now y0 ends up being 2y. That's 2y0. When I substitute y0 in, when I do this integral, I get 1 plus. Now here I'm integrating from 0 to x 2. Then y2, I take 1 plus 2t, substitute in, this is y2 of x. And this time, I will get 1 plus, when I integrate 2, I'll get 2x. When I integrate this one, I will get 2x squared all over 2 factorial, and so on. Now, I could do more of these, but it can be shown by induction that what I get is y sub n is this, 1 plus 2x whole squared over 2 factorial plus, it goes all the way in down to 2x whole to the n over n factorial. But you can see as n goes to infinity, this is the Maclaurin series for e to the 2x. So you see y sub n converges to e to the 2x, which is the solution to this equation. The 8-page Denise's paper is put here, and I encourage you to look at it. You could learn a lot of math looking through it, and she does go through the calculations, and it's really a nice job that she has done. Now, it should be noted that while the technique used in the proof of Picard's theorem is a powerful concept and theoretical tool, it is not a very useful solution tech for numerical approximation. You see, it turns out this converges way too slow. But later on in the course, we will discuss other techniques for numerical solutions, and so we'll cover that later. But this is an important theorem. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself, because self-care is important. And take care of each other too, because we're all in this together. God bless you all.